Mm, So this should be live in any minute. Okay, we are live and we are ready. So let me start. Hi, folks, and welcome back to another Bitbar Kotlin user group session. I'm super happy to be here today. And for those who doesn't know me, I'm Randy, and I'm supporting our good Holger with the group organization videos, etc. Group, basically supporting him. So you will see me from time to time here taking over the sessions. And so today I'm happy to have with me our new guest, Mohit, who will be presenting us an interesting talk in a few seconds. Just wanted to say on the beginning that if you like what you see, press the like button. And if you don't yet, click the subscribe button and follow us for more amazing content. So without any further delays, Mohit, the stage is yours. Take us there.
Thank you. Thank you for having me. So my presentation is about building state flows with Molecule. So my name is Mohit Sarveiya. I'm a Google developer expert in Kotlin and Android. And you could find me on Mastodon. Hey, it's Mohit at androiddev.social. So in this presentation, what we're going to learn about is Molecule is a library. So we're going to learn about how do you use it in Android, like to build presenters. We'll break down different things such as, what's a frame clock? How does it relate to this library? How do you launch like flows? How do you test things? And how does it work internally? So there's a lot to cover. So let's start by looking at what this library is for and how to use it in a practical use case. So what this library is that this library takes in a composable function. So in compose, everything the basic units of in compose are composable functions. So this is a composable function which returns some particular thing, and this library takes this composable function and internally it sets up, the compose runtime, and it provides this composable function. And what it creates and gives back to you is a state flow from coroutines, stream, a hot flow. So whenever a recomposition happens, a recomposition means that this function, composable function, gets called again and has a new result. And when that happens, a result is pushed to the state flow. A new item is pushed to the state flow. And this is the basic overview of what this library does underneath the hood. And this library is useful for creating these flows, these state flows, and hooking them up with Compose. And Compose is not just for UI, it's also, you could use it for other things. So this is an example of a library that's using Compose for things outside of UI. This is using it to build streams. So when it recomposes and it pushes something to state flow, that's all happens by a monatomic frame clock. And this is something that's provided as part of Jetpack, part of Compose. So whenever a frame is sent in this, you could think of the frame like a film, a movie. You're watching a movie, and each image that you see is divided into frames. And whenever a frame is sent, what it does is that it triggers a recomposition, and whatever the result is, when the frame gets sent, it gets pushed to the state flow. And that's important to understand, and we'll get into what this means. in more details. So let's look at a very simple example of building an app, a to-do app that lists to-dos. And what we're going to look at is how do we use this library for a practical example first. So we have a list of to-dos and we can mark them as complete, and we could add new to-dos. So what we're going to do to build this, and we're going to use a pattern. We're going to architect this app in a way. We're going to use a presenter that's going to hold our business logic. And the presenter will communicate with a repository to get, what these to-dos items are. And it will get them in a response. So the presenter will provide the view, communicate with the view, and give it a view model to render. The view model, not to be confused with an Android X view model. The view model is basically a data class. It could also be a seal interface, where the view model just tells the view, like, here are the names of the to-dos, the strings, the state, whether it's completed or not. And it gives it all the information on how to render the UI. And whenever you're on the view, you could also take in events. There events could happen where you could complete a to-do. You could create one, and those are UI events that are propagated also to the presenter. This is our basic setup. And what we'll look at is how our presenter works. How do we hook it up and use this library called Molecule? So when you also look at this, and one thing I want to go over with this, I want to emphasize is that the presenter communicates with the view through a state flow. So what we're going to do first is create a interface called Molecule Presenter that takes in a generic. What is the event that's going to read and the view model that is going to provide to the view. So this interface has a method, composable method called models, which returns a view model. So this is the method that we're going to provide to Molecule to create, and then will give us back a state flow. And this models method takes in a flow of events, like click events that could happen in the UI. So we made this interface so that we could create multiple presenters if we need to, and they could all abide by this contract. So let's look at how to build this very simple presenter for this screen. And in order to build a presenter for this screen, I have created a class called Task List Presenter, which inherits this interface. And I'm going to inject into it, provided a repository to get the task that I want to display in the UI. So I have some repository, and I also need to provide it some types here. So I have task list events and a task list view model. So the event, let's look at first the view model and what that is and how that's built. The view model is a seal class. And this is the view model, again, not to be confused with the Android X view model. This is just a UI model. And what I'm doing here is that I have a seal class, and the UI states that could happen are versus the loading state that could happen. Then you either have a success state with a list of tasks that you want to display. You could also have an empty state. So these are all the different states that my UI will transition from one to the other. So what I also have here is a list of events that my presenter could handle. And this is a sealed interface. The event that I have is that I could click on a task and mark it as completed. When that event occurs, I may want to communicate with the repository, hey, mark this as completed on the back end. So this is our presenter. And what is the logic that we're going to add in our models method? We need to add logic to come up with a specific view model. So the logic that we're going to have in this models method is that first we're going to create a state holder, which is going to have basically the task list view model, and it's null by default. So the first thing that we need to do is to we're going to tell our repository that, hey, get me a list of tasks. And obviously that's an asynchronous, call, and that needs to happen on a launched effect. And inside of a launched effect, I'm telling my repository, get me a list of tasks, making a request. And it gives me some result, which could be either a failure or a success. So in a when, I have two cases. In the success case, I need to be able to take the list of tasks and create, a view model for each row. And that's what I'm going to do here. So in my success case, I'm going to create my task list view model of success. And I'm going to go through all the tasks that I return and map them to a list of task view model. So this is for each row. I have a description there. I also have a Boolean to know whether it was completed or not. So this is information that I'm creating, the view model I'm creating for my view. So next thing that I need to do is the error case, which is I'm going to display, it's going to be an empty state. So it could be an error message, and also that you could display with a retry button also. So this is a very simple example of what's going to be in my models method business logic, and I'm taking the results and I'm assigning my task view model state holder to this new state after communicating with the repository. So let's look at basically this. Let's take a step back and look at this logic. I have my state holder, which is my task view model, and I have a launched effect, basically, where I'm communicating with the repo, and then I'm initializing and I'm providing this value, updating my state holder with this view model. And then I return basically the view model from this method. And whenever it's null, you can see that I'm using Elvis notation there, and it's going to be loading. The task view model will be a loading state. So I have my logic, my model's logic, and using this, I'm going to use Molecule to create a state flow. I'm going to provide this to Molecule. And in order, so we wrote out all the logic for our presenter. So I need a way to be able to provide this to Molecule, and so that it internally could set up a recomposer, and it could internally provide this composable method. And in order to do this library Molecule gives me extensions that I could use. So the first thing that I need to do is create a scope, coroutine scope. And the scope takes in some context. And as you know, you could add different things to a context. And one of the things you could add is a dispatcher. So I'm using a main dispatcher here. And what this library provides is an extension called launch molecule on the scope. And what I'm going to do there is that when I call this method, it returns me a state flow of the task view model. So I'm going to read from this state flow and then provide my view, basically an emission, and an item that was emitted, a view model that was emitted to render. So this launch molecule method takes in a recomposition clock, and I'll go more into what this clock is for and what it means. And I'm using here a context clock. So the other thing that it has is this lambda block. And this is the second parameter that it takes in the launch molecule method, which is a function. So I'm passing in, I'm calling the method, models method, my composable method in there. And anytime this models method produces a new value, it gets pushed to the model state flow. So I'm also going to pass in my list of events from my UI. You could set up this list of events like as a channel, for example, where events are being pushed. and create a flow from it. So what I have, how do I read from this state flow? So I'm going to do scope.launch, and then in an undispatched, I'm going to pass in an undispatched context. And I'm going to read from it by collecting from this models flow, and then I'm going to pass in a model that which is emitted to my task view. So this is something you would do outside of your presenter at the root layer level, where you're going to launch your molecule. And this is the basics of using molecule for our use case. So let's look at basically the next step, which is frame clocks. And when we launched our molecule, we had to provide a recomposition clock called context clock. And what does that mean? You know, what are the clocks that you could use? So what molecule does is that it takes in as just to review, takes in a composable method that you create, which has some return type, and internally sets up the compose. It sets up recomposer. It hooks into compose, and we'll look at how this library does that. And it produces a state flow for you. So it gives you back a state flow. And whenever a recomposition occurs, whenever that composable method I'm giving gets called again, and it's going to give you a new value whenever a frame is being sent by a monatomic frame clock. So when a recomposition occurs, this method gets called again with new inputs, and it produces a new model. And that model gets pushed outwards to the state flow whenever a frame is sent and by this clock. And so how does this work? So there are different types of clocks. There's an immediate clock. There's also a context clock. So let's look at basically how this works. So when I created this coroutine scope, I'm using this main dispatcher. And the dispatcher that I'm using is from this library. And basically, whenever you could pass different things to a coroutine scope and different context elements. So a job dispatcher, you could also give a coroutine a name if you want. And for example, like I could give a name like this, name, coroutine name, and I could just append things to the context by using the plus operator. So so when you look at what main is, what is main? So main is basically a coroutine context that this library has. And internally, it has something called an Android UI dispatcher. And this Android UI dispatcher is actually something that was borrowed or copied from Compose. And the reason why it was copied is because it's actually a general purpose tool, not just something that is specific to Compose UI. So this is a coroutine dispatcher that I'm using. And what it does is that it pulls basically a frame clock out of that. So you can see here that is basically adding to the context using the plus operator or frame clock. And so it's adding that frame clock to your context for your coroutine scope. And this is the frame clock, which is it's a monatomic frame clock, Android UI frame clock. And this frame clock is actually, when you think about what a monatomic frame clock is also a coroutine context element. And it's an interface, so it inherits this coroutine context element. Every coroutine context element inherits this contract, and which has a method with frame nanos. And whenever frame is given, this method is called after a specific time. So whenever you pass in a recomposition clock or context clock, what you're saying is that I want you to fish for the frame clock that has been set up. So as you saw in the previous slides, there's a frame clock that has been set up for you, and it utilizes that one. So A context clock will find the monatomic frame clock out of the calling context. You use it for recomposition. So there is a frame clock that has been set, and I'll go back and show you that slide once again. You can see right there, dispatcher plus dispatcher.frame clock. So it's adding this frame clock, to the context call to the context, and is going to utilize that one. That's what context clock does. Recomposition context clock does, and that's important to understand. So there are two types of recomposition clocks. There is also an immediate, which is a gated frame clock that's useful for testing. And the other, this is the one, these are the two ones. Whenever you're building outside of unit testing, you would commonly use a context clock. So this is what a recomposition clock is and how it works here, what it really means. And let's look at now what this launch molecule method does. The launch molecule method, as I said, is an extension on a scope. And internally, what it does is that it sets up a recomposer, and it provides to the recomposer. Recomposer is a component which is part of Compose, and that libraries could use to hook into things. And what it provides the recomposer it provides it a context. And what it's basically doing is that it's checking which recomposition clock are you using, immediate, or are you specify a context clock. When you look at context clock, it's using an empty coroutine context. That means that the reason why it's doing that is because there's a frame clock that has already been, added to the coroutine context. When it's immediate, this library has a special coroutine context called gated frame clock that it's using that is going to set. And it utilizes this context, and it provides it to something called a recomposer. And that's what it does underneath the hood, this launch molecule method. And it creates a state flow and it gives it back to you. And we'll look at how that works more. So let's look at an example of a test this library has, which emphasizes the importance of a frame clock, and this idea that you need to send a frame in order for you to get a result. So over here, this is a test for just testing that the state flow emits items. And I'm creating a coroutine using run blocking. And I have a dispatcher in here. So the coroutines library provides me some testing utilities I could use. So I have a test coroutine dispatcher. And I also have a frame clock, a broadcast frame clock, which is useful for low-level operations. This broadcast frame clock is provided by Compose that I'm using. So I'm going to create a scope, and I'm going to provide the scope a context, a dispatcher, this test dispatcher, and this clock. So I have my scope, which is ready, already has a frame clock that I have already attached to it. And I'm going to launch a molecule that's going to give me a state flow. I'm going to tell it to use context clock, recomposition clock as context clock. What that's going to do, as we saw earlier, is going to use this frame clock right here, this broadcast frame clock. That's what it's going to use, because I have already set basically that a clock in the context. The next thing that I'm going to do is, for this test, I'm going to update a state, a value. I'm going to update every time a recomposition happens. This value is going to get updated, and I'm going to perform assertions. So one of the methods that launch model, there are a couple of different extensions that we'll look at. One of them has a callback emitter that gets called every time every time a recomposition happens. And what I'm going to do there is that I'm going to update this value. And how does this work? How will I update the value? What does the logic look like? The second parameter of the launch, third parameter in this case of launch molecule is my logic and is my composable function. And previously I was calling my composable function. Over here, I'm going to write out the logic. So I have my state holder for my count, initial value of 0. And I'm going to do a launch effect. Inside of it, I'm going to have a loop that continuously increments that count, but it does so with a initial delay. So how would this work? So first time you go through that method, first time it goes through and the value is going to be 0, right? The initial value is going to be 0 because it go in the initial composition, it goes through and it reads that count is 0, right? And it launches an effect, and then first initially is going to return a count which is a 0. So that's why this assert equals is 0. And then in my launch effect, while the launch effect is running, I need to be able to advance time. I need to be able to tell my dispatcher the advance time, because when it goes in here, it's going to go in this while loop and stop at this delay, because I need to advance that time forward to increment my counter. When I do that, the count value now is 1. So now when I do an assertion, you'll see that my value is 1. But in reality, the value is actually not 1. A recomposition happened, right? A new value was produced, but it won't update my state. It won't call that emitter method because it won't call this emitter method my launch molecule. It goes in here and it increments the value of count, and it won't be a value of 1 because I need to tell my monatomic frame clock to actually send a frame. And when that happens and the recomposition happens, then it's going to emit a value to this state flow. So the clock that I'm using for this test is a broadcast frame clock. And it has a method called send frame that I need to explicitly call to be able to send the frame to pass this test, to get the value from the function and then push it on along to the flow. So that's important. That's the importance of frame clocks, and all that is handled for you when you use context clock and it sets up the frame clock. So that's important to understand. The next thing that we'll look at is different ways that you could launch molecules. And we looked at one way to launch a molecule. First, we created a scope with the main dispatcher, and we called the launch molecule method. But there are different variations of this launch molecule method. We looked at 2 of them so far. One of them we looked at was you provided some recomposition clock, and then the second parameter is where you call your composable method. So, and this gives you back a state flow. So another way to do this is to use something called a context flow. And what it does is that you don't have to, in this case, like set a context clock explicitly. It sets it up for you. And what it provides is not a state flow, but a cold flow or normal regular flow, a cold flow. That's what it creates. So this library, you could use it to create streams which are state flows, but also regular flows as well. So what a context flow clock does internally, it takes in a composable function and it uses something called a channel flow. And recall that a channel flow in coroutines is internally creates a channel, a buffer channel. You could push things to and read things from, and it creates a flow that it returns. So I'm going to call launch molecule in there. I'm going to explicitly for you provided a context clock. And then when the emitter is basically called, I'm going to basically push to this channel that channel flow creates some emission. And the next thing that I'm going to provide to this launch molecule is my composable body. So this is what context flow does underneath the hood. And it provides you with and returns a flow so that you could collect from. Another function is called the immediate clock flow. And as the name suggests, it sets up an immediate clock flow for you, immediate clock for you. And another method that this library has called molecule flow, which basically is very similar to what we previously looked at. And what a molecule flow is that it takes in some clock. And based on that clock, it either calls a method context clock flow or immediate clock flow and creates a flow and gives it back to you. So this function is what's important to look at here is that it's creating a regular flow, cold flow, for not a state flow. So another thing, another launch molecule method this library has is basically it which takes in a emitter. And we looked at before when we were looking at the unit test. And the emitter gets called every time a emission happens. This emitter is going to be updated. It's like a callback. So the emitter, this launch molecule method doesn't provide a state flow for you or any type of flow. It just has a callback, which gets updated every time a recomposition happens. So these are the different methods. Some methods, there are variations here that give you a regular flow versus a launch molecule, which gives you a state flow that you could use. So let's look at basically now, how do you go about testing molecules? So testing molecule, we looked at a very simple use case in this presentation for displaying a list of to-dos, and how do we go about testing that? And what we did for our example was we added logic in this presenter, which took in a repository, and you had logics to create this view model that you're going to give that the view would take it and read from. And it communicates with this repository, and for success and failure, it comes up with a view model, which could be a loading state, a success state, or an empty state. And how do we go about testing this? Testing that this produces the correct states for different actions. So there's a library that you could use called Turbine, which is a library that provides you with an extension on the flow. It's a type of queue-based testing, which allows you to test flows that you could utilize. So the way this library works is that, so one thing before I go into this library is that, why am I using this library? Why is it useful? Is that when I created my models method, I'm going to, as you know, launch a molecule which gives me a state flow. And the state flow is what I want to be able to use Turbine with. I want to be able to test it with. That's why I'm using Turbine, because it's very useful, because I have a state flow, which is what I call the launch molecule method that is returning to me. So let's look at a simple example using Turbine. Turbine is a library. For example, I have a flow here that emits 1 and 2. And test is an extension that this library has that I could use to be able to read from the flow and do assertions. So I'm going to do assert equals 1. I could do this wait item, gives me an emission, and I could do an assertion whether it's a 1 or a 2. And I could verify that the flow actually completed, whether everything was emitted from the flow or not. And the way the test extension works is that it reads from the flow. It reads from the flow, and it puts everything into a channel, emission one by one by one. So you kind of have a record of all the emissions that happen. And you could read from the channel and do assertions one by one. And what it asks to the channel are events, like if something was emitted, event, or complete or not. So collect Turbine in, creates a channel, And what it does is that this collect into channel method, as the name suggests, reads from the flow, puts everything in the channel that you could read from. The channel turbine is kind of like this wrapper, which like kind of has an API that allows you to do like things such as await item, await complete, await event, etc. So it creates an unlimited buffer channel. And what a channel is like it's a blocking queue. And what it does is that it has an API, like it abides by an API. And in there, you're able to read from the channel, await item, for example, events from the channel. That's what that is. So what is this API that Turbine provides? All of the things that you could use in your test, things that you could read from the flow, is this interface called Receive Turbine. And Receive Turbine has events that you saw I'm using in my test, like await event, await error, await item, etc. That's how Turbine works underneath the hood. So when I launch a molecule, and for my example, I do scope.launch molecule, which is giving me a state flow. This is what I'm going to call my test extension on that flow. And I'm also giving it I'm calling the presenters models method, the composable method to it. So this models method, in order to be able to test this, first thing I need to do is create a fake task repository. And I'm going to give it some fake list of task data to it. And basically, the next thing that I'm going to do is provide this task list presenter and give it my fake repository. And what I'm going to do is that I'm going to create a test. And what I'm testing here is the success criteria, the happy path first. And I have a run blocking that I'm using to create a test with. I'm not using run blocking test, I'm not using run test, which is useful for whenever you're dealing with time. But over here, I'm not dealing with time where I need to advance time. That's why I'm using run blocking. So I'm going to launch a molecule, and I'm going to use the immediate clock. And it's going to send a frame once it receives it really, really quickly. Hence, this is why it's called immediate. And I'm going to call the test extension in there. And in there, what I'm going to do is that I want to test this logic out. And what I want to test is a success case. And what that does is that first I'm creating my task view model. So when I call that test method, it starts by executing this composable method that I have here. And I was going to launch an effect. And then first thing that is going to return me is a loading state. The task view model, first initial composition is null. So in this case, this Elvis notation goes to the loading case. And I'm going to do an assertion. Await item is how I pull from the flow. And I'm going to do an assertion that it's loading. The next thing that is going to do, that I could test is when some event, what happens when a certain event happens. So this models method is taking in a flow of events. And I could create an events mutable shared flow. It could be also a channel that you could create. And what I'm going to do basically send to this event for example, a add task or task was completed. Another thing to note here is that I'm passing this event. I could create a flow from there. I could do events.as flow, and I could pass it to this models method. And over here, I'm using a mutable shared flow, and I'm passing that to my models method, that flow of events that I could push things to. I may have logic like navigation logic. I may have some analytics tracking logic or any type of logic, or like a network request, and I could do assertion like what will happen, that do the right things happen when a certain event happens. So first thing that I'm going to do is it's always the first thing, the initial thing that gets emitted is the loading state that I'm going to verify against. then I could verify the success, or if I'm testing failure, I could also verify that. So this is a very simple way to be able to test, molecules. The last thing that I want to go into is how molecule works underneath a hood. How does it create the state flow? What are the things that it hooks into and compose? So the launch molecule is an extension on a coroutine scope, and it's internally setting up something called a recomposer. And what is a recomposer? So first thing what we'll look at is what are the components of the compose compiler runtime that are useful for libraries? How do libraries hook into compose compiler? So there are three components that you'll see in this library that are used. Composer, there's a composition, a recomposer, and an applier. And what are these things? So when you look at Compose is a compiler plugin, and that hooks in, it's a Kotlin compiler plugin, hooks into the Kotlin compiler. And when you look at the Kotlin compiler, you have different phases. You write your code gets parsed into a tree, and then there's an analysis and resolve phase. Then it converts everything into an intermediate representation. And in the compose compiler, when you look at the source code, you'll see that it has different things that are registers for these different phases. It has different things that are registers into. So when you create a compose movement method, like here, I have a greeting method. What it does is that actually this thing here gets, it basically creates a tree. And a compose movement method defines some change you want to make in this tree. And what a compose method also has is that when you create this compose method, like greeting with name, and what it adds, basically the compiler plugin, is that it adds a composer object to it. And it passes this composer object from one composer method to another. And it uses this composer method to be able to define what changes are, to be able to delegate changes. So it passes it to another composer method that's inside there called for example, text, and it passes that same composer along. You'll see this idea also in suspendable functions, where you'll see that the Kotlin compiler actually adds a continuation object, and it passes that along to other methods, like another method, it passes that along. This is the same idea. So what it does is that it defines some change. The composer method emits a change that for your composition tree. So here's an example of, in Compose UI, there's a layout. And you can see here in this example of how it's basically teaching the runtime on what are the changes that need to happen. And it delegates those changes to it. So by using this composer. So you can also see there's a remember method that we saw, and it's also useful that current composer is also used for caching, for example. So what happens is that when a recomposition occurs, it defines a list of changes. It makes a list that define what are the things that need to change in this tree, this composition tree. And you have an applier, hence the word applier, that reads each change and updates, actually materializes a tree and updates the tree. So the change is a type alias, and it defines what are the things that need to change, and has an applier attached to it. The applier goes in and it updates something called a slot table, which is a data structure used to define and compose the tree. And this is an example of an applier for using Compose UI, for example. You can see it has different methods: insert, bottom up, top down, move. And there's a method in which a client library could hook into these things. And there are 3 steps that are followed to create a recomposer, to specify what applier that you want to use, and to provide the composable function that you're using to hook into compose, like this, which is what this library does. You create a composable method that has a return type, and then it uses that and it sets up basically the recomposable method with it. So what is a recomposer? And then what it does is that it triggers recomposition, and you're giving it some context. So internally it creates a coroutine and it determines which thread to compose or recompose on. So for example, in the compose UI example, which is compose UI is actually a library, right? That hooks into the bare core, the core compose runtime, the Kotlin compiler plugin. And it basically follows the same method. You can see here that this right here is creating a recomposer, and it's giving it some context, creating context with the clock. So molecule, similarly in the launch molecule method, it basically sets up as we saw earlier, a context clock. And basically what it does is that it creates a recomposer with it. And the recomposer, because you're giving it a context clock, it's going to create a coroutine, and in the coroutine, it's going to apply the changes that we saw in the changes list. It has the ability to cancel this job when a shutdown occurs. So what this library does is sets up that recomposer, provides a context to it. And it also sets up something called a composition object, in which you're giving it this applier, the applier that you're going to use. For this library, it's very simple. It's a unit applier, so it just doesn't really do anything. And this is a simple use case for this library. And it also registers and starts the recomposer by calling run composition apply changes. So the more important thing to see here is that this composition object is calling set content in there, and it's providing this composable method, this presenters models method that you provide to it. This is the kind of like the bridge that's setting up. Your composable method is setting up a bridge to this compose world. So what's going to happen is that there's a callback emitter. So every time a recomposition happens, like this composable method emits something, is going to push off to this callback a new emission. And then what it does is that it creates a state flow for you underneath the hood. And it's going to push to this state flow a value in this callback that gets emitted. And this state flow is returned to you that you could then collect from. So anytime recomposition happens, this launch molecule method, this emitter is getting called and pushing it to the state flow. So that right there is, it also sets up the snapshot observer. And there are great presentations, other presentations from DroidCon that you could look at, which go more in depth into how a snapshot system works. So externally, when you have the state flow, as we saw, you could collect from it and take the emission and give it to a view. So that's how Molecule works. That's everything about molecules. I hope that was helpful for you. If you want to learn more, check out my website, codingwithmohit.com. You could also find me on Mastodon at heyitsmohit@androiddev.social. Thank you for having me. Thank you, Virtual Kotlin group, and for this opportunity to present at this meetup. Thank you very much.
Excellent, Mohit. Thank you very much again for your awesome presentation. And thanks, folks. You haven't write any questions, so I will give some minutes so you can write it if you have anything. Otherwise, I would just assume that, Mohit, you did a great job and you explained so well that they don't have any question anymore. Then I really would like to also just send me afterwards the presentation or the link to the presentation so we can attach it here to the to the video afterwards. And yes, I think that would be all. So I'm not an Android developer myself, but I really feel that after this conference, I just want to go there and try out, because it seems like very easy to make this composable and state change now using this molecule. It's like, I think I feel like it's not that complicated.
Yeah, for sure. It makes it very easy to set up your presenter, set up the pattern describe makes it really easy to set up state management.
Yeah. So I don't see any questions so far. I guess that will be all. Thanks a lot again, guys, for the awesome for attending to this conference. Sorry. And yes, we have a question from Jaroslav. He asked, when you showed some tests, you use run blocking. Should we use run test?
You could use run test. That has, benefits where you could be able to use such things as run current and run an advanced time. And you could follow a pattern where you only use run test, and so that, yeah, you could use run test.
Okay. I hope that answers your question. And I don't see anything. Yeah, thanks. I don't see any other question coming from the channel. Anyway, if you have any further question later on, just please post it here in the channel or through Twitter, or maybe just reach out to Mohit through the proper channels that he already pointed out. And yeah. Oh, we got another question now from Hamid. Is asking, so what was the difference between them? I guess between the run blocking and the run tests.
So run test is creating a test. Internally, it creates a test coroutine scope. And when it creates that test coroutine scope, it creates it with this test coroutine dispatcher that uses a delay controller. And the delay controller gives you the ability to, it makes it easier where you, for example, suppose you had a test, you were using run test. And rather than explicitly doing dispatcher.advanced time by, I could just call advanced time by internally in my run test method. And what it's going to do is going to tell the delay controller to be able to advance to whenever you're handling virtual time. It makes it easier to handle virtual time. So run blocking, you don't get any of that unless you create your own. You could create your own dispatcher and provide it. That's what I did in my example. I basically created my own scope, provided basically a dispatcher to it, which was a test coroutine dispatcher. And when I'm using run blocking, I'm taking that dispatcher and then I'm basically doing dispatcher.advanced time by. So the way that I did it was the way you would do it previous to run test. So now with the updates with the coroutines library, you would want to use run test whenever you're dealing with virtual time. And if you're not dealing with I use run blocking because it was very simple. I wasn't dealing with virtual time at all when I was testing the presenter. And when you use run blocking, it doesn't really set up a test coroutine dispatcher internally. And those are the differences between those two things. A lot of people, one pattern that's followed now is use run tests for everything, even when you're not even when you're not dealing with virtual time.
Okay.
That's a pattern that some people follow,
Yeah. Do we have any, or do you have any link to a GitHub with an example code so that you can send us, and then we can also post it here to the link?
Yeah, for sure. I made a example app using Molecule, is a multi-platform app. I'll send a link to that.
Nice. I guess if people will really appreciate that, and they can take a look and then try out, and so they don't need to watch through the whole video and just to come up with a
Right.
example app. Yeah, that makes a lot of sense. Then I guess let's wait for a couple of seconds more to see if there is one final questions, or otherwise then I will just finish this session. Hamid say thanks, by the way. And so I guess I'm not getting any other question now. So thanks a lot, guys, for being here today. Thanks a lot, Mohit. And I hope to see you again soon in the channel, like sharing your knowledge and sharing another awesome library, or maybe not library, but patterns, or who knows, maybe some other good tricks and tips and tricks that you have there that makes our lives easier.
Yeah, definitely.
Nice.
Thank you for having me.
Thanks a lot. So have a good one, guys. Bye-bye.